So, there's been a long, wonderful symbiotic relationship between string theory and conformal field theory, and Ming Chang is going to tell us about, I think, one of the most interesting new developments in that field. So, over to you, Ming.
Okay, thank you. So first, I would like to thank the organizers for holding this wonderful meeting, wonderful conference, and also inviting me to speak here. So today, I will introduce to you supercharge cohomology and discuss its relation to black holes. This talk is based on the collaboration with Xi Ying and Yinxuan Lin from Harvard, Jinxiang Wu from Oxford, Li Feng from Northeastern, and my student Yixiao Tao. We have these 5 papers. And also see these 3 papers from people in Korea, and also these 2 papers from people in PI and Boston. And also these 2 previous string talks. Let me begin by give you some motivation for studying supercharge cohomology. And right now, it has been known for 20 years that there are large BPS black holes in ADS5. And of course, we would like to understand their microstate using the dual CFT. And in fact, the n-squared growth of their entropy can be reproduced by the superconformal index. However, given a non-perturbatively complete framework of ADS-CFT, we should be able to answer more refined questions. For example, what are the wave functions and dynamics of these microstates? And another more refined or more specific question might be, how do we distinguish a weakly bound state of n-squared gravitons from typical black hole microstates? And one obstacle of this approach is that holography is a strong-weak duality, and black holes exist at large N and strong top coupling, and are hard to study from the CFT side. And there are commonly 2 ways out. First is to study toy models, such as lower dimensional holography. And the second way would be the focus of my talk, is to focusing on physical quantities that are protected by supersymmetry. And I will show you that supercharge cohomology is a very good quantity in this purpose. And first, it is semi-protected by supersymmetry and reveals much richer information beyond state counting. So let me elaborate these 2 points a bit more. So first, about the semi-protection by supersymmetry. And this is due to a non-renormalization conjecture. It states that supercharge cohomology is invariant along the conformal manifold of the boundary CFT away from free points. So there are mainly 2 evidences for this conjecture. First, we can match the BPS spectrum and infinite and limit, and I will talk about this more later. And the second evidence is about the consistency of this conjecture and with the S-duality of n equals 4 superYAG-MUs, and also the S-duality of n equals 2 theories. And about the new information beyond state counting or superconformal index, first, it contains the complete BPS spectrum information. And in particular, it counts BPS state without the -1 to F. So we know the exact number of BPS states. There's no cancellation between Bosonian and Fermionic states. And furthermore, it also contains information on the wave function of the BPS state, modulo exact terms in the cohomology. And this information can also tell us how BPS states are related in theories at different ranks N. So here is the outline of my talk. First, I will introduce the supercharge cohomology, and then I will discuss a classification of supercharge cohomology into the monotone, or also called graviton cohomology, and also the fortuitous, or also called black hole cohomology. And then I will discuss the bulk duals of the supercharge cohomologies. And finally, I will give a more discussion on the fortuitous cohomology and black holes. First, supercharge cohomology. Supercharge cohomology can be defined very generally. It only needs a supercharge Q that is nilpotent, Q squared equals 0. But the main focus of this talk will be the 4D maximal superYAG-MUs with SUN gauge group. And in this theory, we have 16Q and 16S, and we will pick a pair of Q and S. And then if we take the anti-commutator of Q and S, we get the bosonic charge. And in particular, it is a linear combination of the conformal dimension E and 2 spin, J1, J2, and 3 R charges, Q1, Q2, and Q3. The BPS states are states with delta equals 0. And now, since the supercharge I pick is nilpotent, we can consider the Q cohomology. It's defined as we first take the space of Q closed operators and mod out the space of Q exact operators. And with this, we can now apply a very standard Hodge theory argument, which gives us a 1-to-1 correspondence between Q cohomology classes and BPS states. And this one-to-one correspondence is the same one as the more familiar one-to-one correspondence between the Dirac cohomology classes and harmonic forms. So with this, we can study BPS states by using Q cohomology. And then I will assume the non-renormalization conjecture that says that Q cohomology is independent of G Young mills as long as it is not zero. And this conjecture allows us to compute Q cohomology at weak coupling. At weak coupling, local operators can be written in terms of multi-traces of fundamental fields with covariant derivatives. But we also need to impose the trace relations. Trace relations play a very important role in the study of supercharged cohomology. So here I give a very simple example of a trace relation. Let's consider a 2x2 matrix X, and then it needs to satisfy the following equation. But in general, if we have many different types of bosonic and fermionic matrices, the trace relations can be very complicated. But in this talk, I will only use a very simple property of trace relations. So let me define In to be the space of trace relation at rank n. And then we have In plus 1 is a strict subset of In. So this would tell us that we have fewer trace relations if we go to higher n. And at weak coupling, it also suffices to work with fundamental fields that are BPS in free theory. And it will also be very convenient to assemble these fundamental fields into a superfield. I call it psi. And it's a superfield with 2 bosonic coordinates, Z alpha, and 3 fermionic coordinates, theta I. And in particular, if we expand this superfield in terms of Z alpha and the theta I, the coefficients are, we recover the fundamental fields. So lambdas are gauginos, phi I are complex scalars, psi I are complex fermions, and we also have a self-dual field strength F++. And this dot 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 means the covariant derivative acting on them. And one advantage of writing things in this superfield form is that the Q action takes a very concise form. So Q acting on this superfield psi just gives us psi square. And now if we want to consider multi-traces made out of products of these psis, we just simply use the Leibniz rules with also this simple Q action, and then we can compute the Q action on arbitrary multi-traces. So now let me discuss a classification of the cohomologies into monotone and fortuitous. So let me start with an operator O that represents the Q cohomology class. And now we can write O non-uniquely as a multitrace. I call it O tilde. This means that suppose I have 2 multitraces that differ by a trace relation, and they will give me the same O by using the trace relation. Now, if this particular cohomology class is monotone, or also called graviton cohomology, then Q acting on O tilde will just give me 0 without using any trace relations. And now since O tilde, this multitrace, does not depend on the particular rank n I choose. So I will actually get a sequence of cohomology classes at increasing n. And this will also give me a sequence of BPS operator with increasing n. So it's like this figure show as the blue dots in the left figure. And on the other hand, if this cohomology is fortuitous, or also called black hole cohomology, and then Q acting on O tilde will give me a non-trivial trace relation at some particular n. But now, since we know that there are fewer trace relations at higher n, so if we try to increase n, then up to some point, say up to n star, then Q acting on O tilde will no longer be a trace relation. And in this case, the operator O will be non-Q close and will not give me a Q cohomology. So this tells me that I only have fortuitous cohomology for a certain finite range of n, so as this red dot shows. And so for the monotone one, I have an infinite n limit, but with a fixed with a fixed O tilde. But for the fortuitous one, I do not have an infinite n limit. And note that this large n limit is not the limit that we usually consider if we want to study black hole. In that case, we want to also take the energy to scale with n squared. But if we want to keep energy scale with n squared, then we cannot fix the form of O tilde. And finally, let me mention that The above discussion, I only give you the properties of monotone and fortuitous cohomologies. They shouldn't be taken as definition of them. The precise definition is given by a long exact sequence that can be found in my paper with Yin-Xuan Lin. And also, this long exact sequence also tell me that the Q cohomologies are either monotone or fortuitous. And now let me discuss examples of monotones and fortuitous cohomologies in N=4 super Yang-mills. So first, about the monotone. To construct it, let me consider this formal one-form d psi, and it's a one-form on the superspace, and it can be expanded in terms of dz and d theta. And the previous simple Q action now becomes Q acting on d psi, give me just commutator of psi and d psi. And this also very simple Q action would immediately tell me that if I consider multi-traces of d psi, then it is Q closed and not Q exact without using any trace relations. And in fact, this particular multi-trace form of d psi will give me all the monotone Q cohomologies, and after imposing trace relations at finite n. So next, let me discuss the fortuitous Q cohomologies. Unlike the monotone one, we do not have a formula for all of them, but by a brute force comprehensive search in the SU2 theory up to high spin and R charges, we found the first fortuitous Q cohomology. I have to comment about this. First, it is very hard to find. And go to certain spin and R charges, we in total found roughly 10 to the 5 cohomology classes, but only one of them is fortuitous, and almost all of them are monotone, only one is fortuitous. But this actually doesn't mean that fortuitous are few, as we will see later. If we go to a higher spin and R charges and also higher n, there are many fortuitous cohomologies. And also, after our founding, people in Korea, they found a very simple and explicit representative for this cohomology class, as I show over there. And one thing you may notice is that this cohomology, in order to write it down, I only need to take theta derivative and no zero derivative. And this actually defines a very good sector to work with. It's called BMN sector, that only has theta but no z derivative. And the people in Korea, they perform a more efficient search and in this particular sector and achieve the following result. First, for the SU2 and SU3 gauge group, they found multiple infinite towers of fortuitous cohomologies. And also for SU4, they found the leading fortuitous cohomology. So next, let me discuss the bulk duals of the supercharged cohomologies. Before going to explicit conjectures, let me give you some intuitions for the bulk duals. And so first, while supercharged cohomology is independent of the 12 coupling lambda by the non-renormalization conjecture, we will focus on large lambda and look for bulk duals in supergravity. And let's consider the following limit. So let's take some given classical BPS solution in supergravity and consider the G Newton goes to zero limit. That's the same as the rank n goes to infinity limit. But we want to fix all the spins and R charges, and it will also fix the energy by the BPS condition. Now we would like to take this particular limit for first the smooth horizonless solutions. And it is expected that such solution will remain smooth and horizonless, and actually will eventually become perturbative particles in ADS. And this property is very similar to the monotone cohomologies. But on the other hand, we can take the same limit on the black hole solutions. And if we fix the spin and all the charges, then it means the entropy of the black hole is fixed. Now if we take G Newton to zero limit, and then that tells me the area will go to zero. So the solution becomes a naked singularity, and it's bad in supergravity. So we actually do not have a limit. So this is similar to the fortuitous cohomology. So this intuition led us to have the following conjecture. So first, about the monotone Q cohomology at infinite n. And the conjecture is that they are due to BPS multiparticles in ADS 5 times S5. And the evidence of it is coming from the counting of the previous multi-traces of d psi. And that counting exactly matches with the BPS multi-graviton partition functions in the bulk. So now let us turn to the monotone cohomologies at finite n. And the conjecture is that they are due to quantizations of smooth horizonless solutions in supergravity. And we have less evidence for this one comparing to a previous one. In this case, we need to focus on the Hebb BPS operators, and they are all monotone. And we show that the partition function of the Hebb BPS operator can be exactly reproduced by a quantization of the Lin-Looney-Mardasena geometries that are smooth horizonless Hebb BPS geometries. Now let me turn to the more interesting one, the fortuitous cohomologies. And our previous intuition would suggest that they are due to black holes. So let me give some evidence for that. So first, let me argue the following statement, that there are exponentially more fortuitous Q cohomologies than the monotone ones. And this statement can be turned into a slogan saying that a typical black hole microstate is fortuitous. And so this follows from the bound. So let me give an argument of this statement. And we can bound the number of monotone Q cohomologies. So let me start by the left box. So we have the number of monotone cohomologies at finite n. And then, of course, this number is smaller than the number of monotone cohomologies at infinite n because of trace relations. And the number in the second box is equal to the number of BPS multiparticle states in the bulk, just by our previous conjecture. And then, of course, this number is smaller than the number of all multiparticle states. And now we can try to estimate the number of all multiparticle states by considering their entropy. So the entropy of a gas of free particles goes like the energy to the 9/10, and in ADS5 times S5. So we have E to the energy to the 9/10. And now if we are interested in black holes, we are interested in energy scale like n squared. So we have E to the n to the 9/5. And on the other hand, we can consider the growth of total number of all BPS states. And this number can be estimated by the superconformal index. So we have the number of monotones plus the number of fortuitous that equals to the number of all BPS states, and like scale like E to the n squared. And of course, E to the n squared is much larger than, exponentially much larger than E to the n to the 9/5. So we have the statement that there are exponentially more fortuitous Q cohomologies than the monotone ones. And the typical black hole microstate is fortuitous. So let me tell you a bit more on the relation between fortuitous cohomologies and black holes. So let us consider near BPS states above a fortuitous state. And since we consider non-BPS states, so it depends on the top coupling. And we will first consider small top coupling lambda and small n. And now let's try to construct the Hilbert space of these near BPS states. So let's start with an operator O that represents the previous fortuitous cohomology in SU2 super Young mills. And now we can add all possible, we can add to O all possible Q exact terms with the same spins and R charges, and also classical dimensions as O. So this gives me a Hilbert space. And on this Hilbert space, there is a one-loop Hamiltonian acting on it. That's just simply given by any commutator of Q and Q dagger. And the ground state of this one-loop Hamiltonian is the one-loop BPS states that are corresponding to this fortuitous cohomology. And besides the ground state, there are also non-BPS states, and their spectrum are given by this left plot. And the plot on the right. And we see that there are in total 186 states with the density of state plotting there. And one very interesting feature we can see from the plot is that there's a gap between the BPS states of black hole and also all the non-BPS states. And we can also compute the ratio between the gap and the average spacing, and it roughly equals to 32. And now we can consider large top coupling lambda and large n. And in this case, the near BPS spectrum can be obtained by looking at the JT supergravity on the near horizon ADS2 of the BPS black hole. And it has been found that there is a gap of order n to the -2 above the BPS state in the near BPS spectrum. And we can also compute the ratio between the gap and the average spacing. So in this case, we have n to the minus 2 in the numerator. And since they are roughly e to the n squared state, so the average spacing will be roughly e to the minus n squared. And now if we just naively plug in n equals 2, we get 14. And this number is of the same order as the previous number. So there is a similarity between the gap at small top coupling and also large top coupling. So finally, let me end by mentioning some future directions. I think the most interesting question is what is the Borg dual of an individual fortuitous BPS state? And I think this question is the same question as the following question: what is a typical black hole microstate? And of course, to answer this question, we need to construct more fortuitous Q cohomologies at larger n. And so far, we only have data for n equals 2, 3, and 4. But I would like to argue that we actually do not need to go to very high n. I think if n is roughly greater than 6 might be enough. So this intuition is coming from if we consider the ratio between the entropy and the n squared computed from the superconformal index. And this ratio already shows convergence at roughly n equals 6. So I would expect that we will start learning interesting things about black holes from fortuitous cohomologies if we go above n equals 6. And then I have a proposal for the answer of the question, the proposal for the Borg dual of a fortuitous BPS state. And that is, it may correspond to a coupled system of d bands in supergravity background at strong top coupling. And the key word here is the strong top coupling. So this makes this proposal different from the standard Strominger-Vafa paradigm that describing black holes as d bands at weak top coupling. And another direction is to study generalizations of Q cohomologies in other systems. For example, D1, D5 CFT, 4D n equals 2 SCFTs, and also the BNN matrix quantum mechanics. And finally, let me end by saying that there is much more to be learned about black holes from supercharged cohomology. Thank you.
Questions? Over here.
So you were explaining how the fortuitous cohomology at large but finite n is dual to a quantization of the Maldacena-Lunin geometry.
Yes.
Right? You were also
no, that's for monotone.
Sorry?
I think you mean monotone or fortuitous?
I mean the fortuitous. That's the black hole microstate, right?
Oh, okay.
Yeah. So what I wanted to ask is, for the fortuitous, take a fortuitous state, send n to infinity. At some point, the state is no longer BPS.
Yes.
Do you see anything interesting in the Borg dual? So the dual geometry is no longer BPS, or what happens if I look at one state and then I send the infinite n limit?
I think maybe you are asking about this intuition part. I think the thing happened is that I want to fix all the R charges and spins, and so if the state go above BPS bound, that means I cannot fix the energy anymore. And so this means that if I take the G Newton go to zero limit, the energy would go above BPS bound, and then I think that would make maybe the entropy also increase, so you actually do not get a naked singularity.
But there's no way to see something in the bulk geometry that would signal that transition.
Yeah, I do not know explicitly how to see that in bulk.
Okay, thanks.
Okay.
Hi, Jimmy. If you if you extrapolate your results to larger values of n, do you expect to see a 5-parameter set of cohomologies? Do you expect your cohomologies to occur basically at every charge, or only on a codimension 1 submanifold in the space of charges? As you know, black holes have this.
Yes. For the supercharged cohomology, we see the 5 parameters. Yes. And the cohomology cars are not localized in any codimension 1 plane.
Any other questions? Sorry. Oh,
So is there a general understanding of what kind of equations would lead to the photolysis phenomena? For example, how many letters do you need in order to have this phenomenon?
That I do not really know. I think you need to turn on. Okay, first you need to go to high enough spin and R charges, and you can also not just put all the spin and R charges to certain particular spin and R charge. You need to turn all them on, and what's the detailed thing about? Yeah, that I do not know.
Any further questions? Yeah, back there.
Thanks for the very nice talk. I had a question about your estimate of n to the 9/5.
Yes.
Don't you need to be a little bit careful here, because the point is that the number of low energy states grows faster with energy than the number of black hole states. So if you plug in, for example, E goes like n to the 4th, which you're allowed to do, that's a very big black hole, then you would get more low energy states, right?
Yes. So here the reason is that maybe that work? Okay. So up to maybe I point here. So here this number depends on n, but all these three numbers are n-independent, because here I've already taken the infinite n limit, so that only depends on energy E. But then finally I would like to look at this particular region, that because I'm interested in black hole, so that I plug E of order n square. So that's why I pick E of order n square.
Yeah, so that's a black hole of ADS size, but you could take a black hole much bigger than the ADS scale, and then you would get a much faster growth of the low energy states, if you want. Typically, there's too many low energy states. It gets reduced.
Maybe, yeah. And also, I mean, this bond is actually a very loose bond. It's quite easy to make it, to get the stronger bond.
Thanks.
Any further questions? I might, since we've got a couple of minutes left, I might abuse my privileges as the chairman and just remark, there's a beautiful conformal field theory discussion of by Denef and Moore, the quiver gauge theories, where almost certainly the exponential number of microstates, BPS states in this thing, are fortuitous. And it'd be really nice to have a discussion of how that works. So there's a homework problem.
Okay, thank you.
Any other questions? Okay, let's thank Ming again.